Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and I'm here with Victor. Before we dive into today's topic, we'd love to hear from you. If you're enjoying our podcast, please take a moment to rate us on your favorite podcast platform. Your support means the world to us.
Absolutely, Sheila. Your feedback helps us improve and reach more developers interested in decentralized systems. Now let's jump into our content for today. We're wrapping up Chapter 4 on decentralized storage systems with a comprehensive summary of what we've covered.
That's right, Victor. But before we start, I have a tricky quiz question for our listeners. Here it is. In the context of decentralized storage systems, what does the P in CAP theorem stand for? And why is it particularly challenging in P2P networks?
Ooh, that's a great question, Sheila. It really gets to the heart of one of the key challenges in distributed systems. I'm sure our listeners will need to think carefully about this one. The CAP theorem is fundamental to understanding the trade-offs in decentralized storage, and the P is especially intriguing in the peer-to-peer context. Let's give our listeners some time to ponder that while we recap our chapter.
Sounds good, Victor. Let's start with the basics. Can you remind us what we mean by decentralized storage systems?
Certainly, decentralized storage systems are a way of storing and retrieving data across a network of peer nodes, rather than relying on a central server. The main idea is to distribute data across multiple locations, improving resilience, scalability, and sometimes privacy.
I see. So it's like instead of keeping all your eggs in one basket, you're spreading them out across many baskets.
That's a great analogy, Sheila. And just like with eggs, we need to be careful about how we handle and distribute our data. This brings us to one of the key concepts we discussed: data replication strategies.
Right. I remember we talked about different ways to replicate data. Can you refresh our memory on why this is important and what some of the strategies are?
Of course, data replication is crucial for ensuring data availability and fault tolerance. We discussed strategies like full replication, where every node has a complete copy of the data, and partial replication, where data is distributed across nodes based on certain criteria. Each strategy has its trade-offs in terms of storage efficiency, network usage, and data availability.
That makes sense. And I recall we also talked about consistency models. There was strong consistency and eventual consistency, right? What's the difference between these?
You've got it, Sheila. Strong consistency ensures that all nodes see the same data at the same time, which is great for accuracy but can be slow and difficult to achieve in distributed systems. Eventual consistency, on the other hand, allows for temporary inconsistencies, but guarantees that all nodes will eventually have the same data. This is often faster and more scalable, but it means you might sometimes get outdated information.
I see. And this ties into the CAP theorem we mentioned earlier, doesn't it?
Absolutely. The CAP theorem states that in a distributed system, you can only have 2 out of 3 guarantees: consistency, availability, and partition tolerance. In P2P networks, partition tolerance is often a must-have, so we're usually choosing between consistency and availability.
That's fascinating. We also covered some real-world implementations, didn't we? I remember us talking about IPFS, the interplanetary file system. What makes it special?
IPFS is a great example of decentralized storage in action. It uses content addressing instead of location addressing, meaning files are identified by their content rather than where they're stored. This allows for deduplication of data across the network and makes it resistant to censorship. It's been used for various applications, from website hosting to large dataset storage.
That's really cool. Before we wrap up, could you quickly touch on data retrieval strategies in these systems?
Certainly, data retrieval in decentralized systems often involves techniques like distributed hash tables, or DHTs, to efficiently locate data. DHTs are like a decentralized phone book that helps nodes find where specific data is stored. Various routing algorithms are then used to find the shortest path to the data. Some systems also use caching strategies to improve retrieval speed for frequently accessed data.
Thanks, Victor. That's a great summary of what we've covered. Now I think it's time to reveal the answer to our quiz question. The P in KP theorem stands for partition tolerance, which is the ability of the system to continue operating despite network partitions. This is particularly challenging in P2P networks because nodes can join and leave the network at any time, potentially causing frequent network partitions.
Excellent explanation, Sheila, and it really underscores why partition tolerance is often non-negotiable in P2P systems, forcing us to make tough choices between consistency and availability.
Indeed it does. Well, that wraps up our chapter on decentralized storage systems. We hope you found this summary helpful. Remember, if you want to dive deeper into these topics, visit crashcasts.com for additional resources. And don't forget to join our Discord community to discuss these concepts with fellow developers.
Absolutely. And if you're finding value in our content, please consider supporting us on Patreon. Your support helps us continue producing high-quality, in-depth content on decentralized application development. Until next time, happy coding!